get up here, I'll get started. In the meantime, watch the pictures of the aurora.
Where is that?
That's from Fairbanks, Alaska. Actually, Alaska, a research range. And this was done in the 80s. They made some high definition, at the time, high definition color television images of the aurora over many nights. And it's really neat.
What color is that?
Space weather. That's pretty much the idea, I believe. And that is charged particles from the Earth's magnetosphere streaming into the atmosphere and exciting the atmosphere, making it off light. So it happens at the poles. We'll talk more about it.
I don't think so.
All right. Why don't we get started? Welcome to a LASP public lecture series. Tonight's talk by me. And I'll be talking about space weather and what it is, how vulnerable are we. How many of you have been to LASP before? Most of you. Have been to public lectures? Work here? Work with us from another lab? Well, I know there are some people in the audience who can correct me on some of the mistakes I'll probably make. If you wish, or you can ask clarifying questions, offer clarifying answers. And if I'm talking over anybody's head, just stop me and I'll try to explain. I have enough slides to talk for several hours, so we'll try not to get too deeply into it, since it is a public lecture, not a university course lasting a semester. So who am I? My name is Frank Eparvier. I'm a research scientist here at LASP. LASP is the Laboratory for Atmospheric and Space Physics, as you probably know. My training was in aeronomy, which is the study of how energy inputs change the atmosphere of the Earth or other planets. I'm an experimentalist, which means I like to measure things, because my mantra is that experiment is the test of all knowledge. We can have as many theories as we want, but until we can run an experiment on them, or making an observation to demonstrate pros or cons about those theories, we really can't say anything about the reality. I currently work with instruments that measure the sun, because the sun is a primary driver of the Earth's atmosphere. I'm a co-investigator on a satellite instrument called the Solar EUV experiment. I'm also a co-investigator on another satellite experiment called the UV variability experiment. That satellite, the Solar Dynamics Observatory, is about to launch sometime this fall, hopefully November. I'm also the lead scientist, principal investigator on an instrument on the GOES series of satellites. GOES is not a research satellite, but it's actually operated by NOAA, and it's an operational satellite. GOES is the satellite or set of satellites that give you all the weather images that you see on the news, but they also have space weather instruments. And the X's, which stands for EUV and X-ray radiance sensors, are a set of instruments that stare at the sun and make measurements of the brightness of the sun and how it varies. I'm here to storytell, basically. I'm going to tell several stories. One is a personal story, how I got into this whole business. The second one is a historical event, a true story. Well, they're all sort of true. The third story is a story of the present day, and we'll talk about space weather and the space weather event and how that affects us today as opposed to historically. And then I'll move into the less true but speculative future musing, talking about what would happen if we have a perfect storm type of space weather event, and how the impacts on today's world would handle that. And finally, I'll have a little bit about what we're doing to prepare for events like that perfect storm. probably run out of time right about here. I hope to get to here. And you can help me along by interrupting me and telling me to shut up and move on to the next slide. So my personal story starts with a kid, actually not so much of a kid, but it feels like about more than half my lifetime ago, when I was an undergraduate at the University of Wisconsin and growing up in Wisconsin. I was home for summer break in August of 1983. I was working the night shift at a candle factory in Oshkosh, Wisconsin. And I was driving home that night, a nice country road right on the side of Lake Winnebago, beautiful view of the sky, hardly a cloud to be seen. Very dark because it was rural. And I looked up and I saw lights in the sky, lights that looked like these lights. In fact, this is a picture not from Wisconsin, but looks very much like what I saw. And being a budding astronomer, being a science major, I had in the back of my car binoculars and a chase lounge that I pulled over and sat in a farmer's field for about 8 hours that night and watched the aurora. And these were the northern lights that my mother had talked about. She had seen them growing up in northern Wisconsin as just a dim glow on the horizon to the north. But this was something that was filling my sky. I could look, and everywhere I looked, in every direction, there were lights flickering and shining and changing. And that started my personal journey on the road to doing space weather. I was fascinated. At the time, I was a physics major and figured, okay, I'll do high energy physics, I'll do fusion studies or particle studies or something. I didn't think that I would get involved in atmospheric research or solar research. But seeing something like this in real life really moves you and changes you. Later on, as a graduate student here at CU in the later 80s, I got to go up to Alaska where they did this and launched a few rockets studying the effects of the aurora on the atmosphere. And I was there in March of 1989 when a truly huge geomagnetic storm occurred, and the aurora were just absolutely amazing. Filled the sky. In fact, I was flying in a plane home and looked out the window. They shut off all the lights, and we looked out the window and saw the auroral oval to the south of us, which means that the activity level was really, really high, because usually the aurora are to the north, even in Alaska. So now we'll move on to somebody else's story. This is the story of Richard Carrington, way back in 1859. He was a British astronomer, a solar scientist, and he was sitting in his little observatory here. There are no pictures of this man. I searched the web, and all I found were things saying, there are no pictures of Richard Carrington. But there is an etching of his observatory. It was a private observatory. And he would go in there every day. He had I think it was an 11 or 12-inch telescope. He would project the sun. He didn't look at it with his eye. He would project the sun onto a screen on the wall. And he would take sketches of what he saw. And he was sitting there in the morning, almost noon, watching a sunspot group and making drawings of it. When suddenly, 2 spots on the sunspot group got really, really bright. In fact, brighter than everything else, washed out everything else that he was looking at. And he got really excited. And he ran off and found somebody else to verify it. And they came running in, and they watched as these 2 spots got brighter and then faded away. And it was just a normal sunspot group. And that was the first real observation of a solar flare. And it had to have been a very, very big solar flare because you can see it in white light. White light flares are very rare. Mostly we detect solar flares in the X-rays, where they're the brightest. But Carrington saw this flare, and we call it the Carrington event, in white light, which means it was really energetic. He probably saw something like this. This is an X-rays, but he was looking at a region that was a sunspot, and he just saw parts of it get brighter and brighter and then dim away. It was gone after 5 minutes. However, he did find the one person to run in and see it, and there was one other person in the world who saw it. And so they published a bunch of papers, and it got to be known as the Carrington event. Now, there wasn't just a flare. The next day, all heck broke loose on the earth. There were telegraph operators all over the world, mostly in Europe and the United States, that had major problems. Normally, telegraph operators need a power source to send their signals down the wires. That day, they didn't. In fact, there were such huge power surges that they could not only communicate with each other for longer distances, but the power surges caused sparks to fly and their equipment to explode. And some telegraph stations even burned down around the country. We also that night saw the aurora. And the aurora is considered something that's usually polar at high latitudes. We call it the northern lights or the southern lights if you live in the south, southern pole. But they weren't relegated just to Alaska and Canada and Scandinavia. They were down around mid-latitudes, even lower latitudes. People in the Caribbean saw the aurora. People in the Mediterranean saw the aurora. People in Hong Kong and Singapore saw the aurora. Now, at the time, Carrington and a few other people speculated that the two events had a lot to do with each other. That the event on the sun that he witnessed was causing somehow the event on the Earth. Now, a lot of the big name scientists at the time poo-pooed that idea. They said, no way, there's absolutely no way that anything happening on the sun can affect anything happening on the Earth. It's full of space in between, and nothing can get through except maybe light. And a little bit of light isn't going to change anything. Well, now we know that Carrington was right, and the experts were wrong. So we understand now that the sun and the Earth are a complex, interconnected system. And we call that system space weather. And here's a drawing of space weather. I expect letting in. You should all understand that everything is drawing. Showing how the sun and the Earth and the Earth's magnetic field and the solar wind and the CMEs and flares and everything interact and all go towards giving us space weather and becoming space weather. So this one diagram is actually many, many semesters of a space weather course if you want to sign up for one. So now we'll talk about what space weather really is and how it can really affect us today. So the story, as usual, starts at the sun. The sun gives off energy and is the primary energy source for the Earth. It gives off light, all wavelengths, from X-rays up to the radio waves, infrared, microwaves, ultraviolet, visible light. It's all coming from the sun and shining on the Earth. But the sun also gives off other things, not just light. It gives off charged particles and magnetic fields. We call that combination of charged particles and magnetic fields streaming out from the sun the solar wind. Now the sun is constantly changing. It's not a static thing. We watch the sun and it varies in all of its output and its structure even constantly on all time scales, from seconds to centuries, millennia, longer. And it changes on all size scales, from the smallest size scale that we've ever observed to the largest size scale of the sun itself and beyond. Here are just some examples. These are solar granules. The sun itself is a hot, seething ball of plasma and atoms and molecules, and it has convection. This is like boiling on the surface of the sun. Each one of these is a convection cell with material rising up in the middle and falling down at the edges. Each one of these granules or convection cells is about the size of the state of Texas. And this is, here's a clock that shows you we're looking at maybe an hour of time. So the sun is changing very rapidly at its surface and interior. Now you're all familiar with the term sunspots. Well, sunspot is basically a spot, yes, a location on the sun where magnetic fields come out of the surface of the sun and re-enter the surface of the sun. And it changes the temperature and the densities in that specific spot. And in the visible, it looks like a dark spot. That's why we call it a sunspot. But at other wavelengths, when we look in ultraviolet or X-rays, this is actually, sunspots are actually very bright. They give off more light, not less. And we can look at activity on other scales at other wavelengths. This is a movie from the TRACE satellite, which is looking in soft X-rays. And you see that there are obviously a lot of magnetic fields on the sun, and that is moving the material of the sun, charged particles, plasma, around and heating it up, cooling it off, and they're constantly changing. You can watch the clock, and we're looking at maybe an hour time variation again. And you see material rising up, falling down, moving around, bits of it bursting out, flying off into space. The solar variability is happening on all time scales, as I said. You can watch this image. This is the sun rotating in the extreme ultraviolet. This is a video taken by the SOHO satellite, instrument on SOHO satellite, which is sitting staring at the sun, taking movies, essentially, at different wavelengths. And here we see sunspots, which are called active regions in the ultraviolet and X-rays, and they're bright. They're much brighter than the surrounding sun. The sun rotates on a time scale of about a month, 27 days relative to the Earth. And so these sunspots, which can last months, several months in a row, rotate around. You can see that they're much brighter than the rest of the sun. So as they rotate around, the amount of sunlight in the ultraviolet reaching the Earth changes. It's kind of like the lighthouse effect, where you've got a bright beacon and it's rotating around. And if you're the Earth, you see it get brighter and dimmer, and it comes back around the next month and brighter and dimmer. So you get monthly variability at the Earth. But this movie also shows sunspots changing on time scales of days, just a few days. And sometimes even you see things like bright flares that just occurred. A real bright flash when suddenly one spot on the sun is brighter than all the rest of the sun combined. But that only lasts for a few minutes or hours. Here's another movie, a different wavelength of a flare. Let's see if I'll play again. So you see brightening here, and then suddenly stuff shoots off. The stuff that shoots off is other material. It's some of this plasma that gets suddenly erupted from the surface of the sun associated with the flare. We call that a coronal mass ejection. The corona is the outer atmosphere of the sun. And mass ejection, of course, is just a lot of stuff flying off. CMEs were really first discovered in the late 80s and early 90s when we started flying satellites, looking at the sun, and blocking out the brightness of the sun. This is a composite image of several images where they blocked out the bright sun and taking pictures of the dim stuff spewing out. And if we string them all together and make a movie, this is actually a movie of the solar wind. This material constantly streaming out from the sun along magnetic field lines. And occasionally when you get flares followed by coronal mass ejection, CMEs, you'll see a big burst of material shooting out. And sometimes that material heads towards the Earth and interacts with the Earth and causes space weather effects. In fact, if we go back to, let's see, let's play this one again. Watch when the flare goes off, suddenly you see a lot of snow in the picture. That snow is actually charged particles that have been shot off by the sun, and they're hitting the detector on the satellite and causing noise in the image. So the sun goes through many activity cycles over different time scales. You're probably most familiar with one that everybody just calls the solar cycle. It's an 11-year cycle, roughly, on average, where the sun goes from being very quiet, very few sunspots, very few active regions, very few CMEs coming off, very few flares, and then gradually over time the sun becomes spottier, more complicated, more active until you get to solar maximum levels, and that takes 3 or 4 years. And suddenly, not suddenly, but over that time, you have lots of sunspots, very frequent solar flares, some of them very large, and lots of coronal mass ejections coming off the sun. And that cycle repeats itself over and over again, roughly 11 years. Not exactly, sometimes it's longer, sometimes it's shorter. If you look at this plot, it's a picture of sunspot numbers, basically, how many sunspots are on the face of the sun over time. And we're looking at 4 centuries here. We're currently just off the edge on another cycle. And you can see that it repeats, but sometimes there are lots of sunspots, and sometimes there are very few sunspots at the maximum of the sunspot cycle. In fact, there are times back in the late 1600s and so when there were very few sunspots at all. Right now, we're at a fairly maximum time of sunspot activity during our solar maxima, and even though we're currently at a solar minimum, where the sun is very, very dim in terms of sunspots, there's very little activity. We've been in the solar minimum for a couple of years now, actually. We expect to come back out of it any time and head towards another solar maximum. Lots of debate in the community whether it'll be a big maximum or a little maximum, or if we're going into a low activity period or even a no activity period. That's all part of the roll in the dice of prediction of solar activity. So right now we don't have hardly any sunspots. There hasn't been any sunspots in months, and we don't have CMEs. We just have nice solar wind streaming out and quiet sunlight. So how does all this affect the Earth? Sunlight in the ultraviolet and X-rays are absorbed in the Earth's upper atmosphere. And this is a plot of altitude above the Earth's atmosphere and wavelength in nanometers. And this is all in the extreme ultraviolet and regular ultraviolet. Visible light is up here from 400 to 700 nanometers. That all makes it to the surface. But the shorter wavelengths you go, the higher in the atmosphere the sunlight is absorbed. At the higher parts of the atmosphere, above 100 kilometers or so, the most energetic light, the extreme ultraviolet and X-rays, are absorbed into the atmosphere. And that goes to heat the upper atmosphere. We're depositing energy into the upper atmosphere, it warms up. It creates what we call the thermosphere, the hotosphere, essentially. It also goes to ionize the upper atmosphere. The upper atmosphere is mostly atoms, a few molecules, but this energetic light comes and it knocks electrons off those atoms and molecules and creates ions and free electrons floating around. We call that part of the atmosphere the ionosphere. So at the top of the atmosphere we have neutrals, which are being heated, but we also have ionized gases, basically, in the upper atmosphere. And any changes in the amount of the extreme ultraviolet and X-rays from the sun cause changes in the upper atmosphere. Animations are working. So let's talk about the photon effects. We'll talk about other effects from space weather, but right now let's concentrate just on the changes in light affecting the Earth. So increased light from the sun means that you get heating of the upper atmosphere. So temperatures at say 200 kilometers above the surface of the Earth can range anywhere from 500 Kelvin up to 1500 Kelvin, depending on whether we're at solar maximum or solar minimum, whether there's a little or a lot of solar activity sending more or less light. And those changes can happen fairly rapidly, on the order of days or over a month, where the atmosphere will heat up and then cool down again as the sun gets dimmer with the monthly activity. What happens with the changing heating of the upper atmosphere is that it expands. Hot gas rises. Basically, you heat something up and it expands. You heat up the Earth's atmosphere and it expands. And what that means is at a specific altitude, say 200 kilometers above the surface, if you have more light from the sun, the atmosphere heats up and the density at that altitude increases. Now remember that, because it's important for what I'm going to talk about next. Here's a plot from, I think it's originally from Google Earth, but I stole it from the satellite operations website. This is a plot showing all the satellites in orbit around the Earth. You can see satellites way out at geosynchronous orbit. That's what this is. Those are mostly communication satellites, some research satellites. They like geosynchronous orbit because the orbital time is the same as the rotation of the Earth, so the satellite just sits over one spot on the Earth constantly, rotates around. And so you can use it for very well for communication and for the imaging of the Earth and things like that. But you'll see nested down here lots and lots of satellites in low Earth orbit. They're actually essentially flying in the upper atmosphere, anywhere from 300 to 1,000 kilometers in altitude. And they're actually flying through the thermosphere, through the upper parts of the ionosphere. Now this plot is showing about 8,000 satellites. We've launched about 8,000 artificial satellites into orbit around the Earth. Most of them are dead. Only about 1,000, I think, are actually still operating. But NORAD tracks all of them because they need to know where every object in space is, because if they want to put up another one, they don't want to have it in an orbit that it runs into each other. In fact, we just recently had a collision between two satellites over the pole, and people don't like that. But that collision and other collisions have caused a lot of space debris also. So NORAD is tracking about 11,000 objects, larger than the size of a softball. And they're all flying, orbiting the Earth. Some of them are operating satellites, some of them are just junk. And they all need to be tracked so that we know that we won't have collisions. So remember what I said about the atmosphere expanding when the sunlight heats it. And when you have more sunlight, the atmosphere gets larger, and satellites flying through that upper atmosphere feel drag. And what happens when you feel drag? You slow down. It's essentially friction. It's flying through a thicker atmosphere, and it slows down. When a satellite slows down, it drops to a lower orbit. And so a thicker atmosphere from solar activity means more drag. More drags means satellites drop in altitude. And if satellites get too low, if they're flying through too thick of an atmosphere, eventually they'll fall down. So satellite drag limits the lifetime of low Earth orbiting satellites. Increased solar activity increases the amount of satellite drag and can make satellites fall down months, if not years, earlier than originally planned. This is a plot that shows on one scale solar activity. So this is just, the red line is just a measurement of the sun varying. You see the monthly variation caused by that beacon effect. So here there were sunspot groups that were coming around visible to the Earth, and then going around the other side and coming back. And the black line is the rate of decay of a satellite orbit. So it's not the altitude of the satellite, but it's a change in altitude of the satellite per day, in meters per day. So just because of this monthly solar activity, you see the satellite dropping by 2, 3, 4, even 6 meters in a day. Most satellites can't recover from that. Things like the International Space Station, which is flying at very low Earth orbit altitudes, I think they're at 350 kilometers or so, they have rockets on it to boost it up because it's constantly falling down. And if there's more solar activity, they fall down more than they want and they boost it back up again. So they're constantly readjusting their altitude. But most other satellites can't do that. They're just designed to last so many years and then they re-enter if they're low Earth orbit. Now the last plot I showed you showed monthly variability of the sun and how it affects satellites and satellite drag. Flares also can affect satellites. A flare going off, a very large flare, remember I said a flare can be brighter in the X-rays and extreme ultraviolet than the entire rest of the sun by orders of magnitude. That all gets absorbed by the Earth's atmosphere. It takes about 8.5 minutes for that light to get to the Earth. And it takes minutes, if not hours, for the atmosphere to react to that. And this is an image showing the black line is a solar flare going off in X-rays. The colored contours are a plot of the density of the atmosphere at a specific altitude. I think, I forget whether it's 500 kilometers or so, 490 kilometers. And so you can see they're chugging along. This is covering about 2.5 days here in time. So this is latitude and this is time. And the blue and the green are the normal densities of the atmosphere. It's more dense at mid and low latitudes because that's where the sun is shining. It's that part of the atmosphere up, so it rises up, it bulges out at the subsolar point. Suddenly the flare goes on. Suddenly also the density increases by a factor of 2 or even 3 at those mid latitudes beneath the sun, directly beneath the sun. Gradually the atmosphere recovers because that input goes away. But during that time, satellites can drop tens or even hundreds of meters within a few hours. Not over days or a month, but within a few hours. That wreaks havoc at NORAD. And they're tracking several hundred objects, or even 1,000 objects in low Earth orbit, and suddenly they're all not where they expected them to be. Most of the tracking is done on a few hours or even a daily basis, where they see a satellite and then they do a model and predict where it's going to be the next time they see it. If a flare goes off and they don't have that flare in their model for the Earth's atmosphere, then that satellite won't be where they thought it would be the next time it comes around, and they have to hunt for it. And so suddenly they lose where are all these satellites. It takes time to find them and re-plot out the courses of those satellites. Now this is a very big flare. This is one of the largest we've seen since the beginning of the space age. This was from October 2003. So this size flares occur on the order of maybe once a year or once a decade, not all the time. Now, moving away from the neutral atmosphere effect, the density effects, let's talk about the ionosphere. Remember, the ionosphere is that part of the atmosphere that has a lot of ions in it. Sunlight knocks off electrons. It's a charged part of the upper atmosphere, essentially. Now that we use that part of the upper atmosphere. The projector is missing my ionosphere. There's a colored band in here that's on my screen, but not on this screen. So imagine, if you will, the ionosphere going through right about here. That's the portion of the atmosphere ionized by the sunlight. So it's primarily on the daylight side. At night, the atmosphere is much less ionized. There's a little bit of residual that lasts through the night, a little bit caused by other things, like starlight and stuff. But most of the time, most of the ionosphere is on the daylight side. We use the ionosphere for a lot of things. We use it to bounce radio waves off of. It acts like a mirror to radio waves, essentially. It's a shell, if you will, above us that we can bounce radio waves off of, and they can come back down to another station from the transmitter to the station over the curve of the Earth that you couldn't regularly just transmit straight to. So if the height of the ionosphere changes, that's due to solar activity. If the atmosphere is expanding, it's absorbed higher up rather than lower. You get changes in how far you can transmit things. If it comes down deeper, you can no longer talk to stations that you used to be able to talk to when the ionosphere was higher. You hear this a lot. Those of you who are old enough to remember AM radio, listen to it, would remember that you drive around at night and you hear a lot of stations from very far away. Because at night the ionosphere is much thinner, the reflection is much higher up, and so you're seeing further around the Earth. In Wisconsin, I remember hearing radio stations from Los Angeles at night. In the daytime, I could barely hear radio stations from Wisconsin. We also use the ionosphere, well, we don't use it, but the ionosphere is there in the way for communications with satellites. It's the medium through which radio waves travel from space to Earth and Earth to space. And if the ionosphere is changing, it can affect how that transmission occurs. If you have more ionization, you have more refraction in the atmosphere and more absorption. We already talked a little bit about reflection. And you can also get an effect called scintillation when the ionosphere is very blobby. We'll talk about that, each one of these separately. So if we have a satellite in space and we're talking to it from Earth and vice versa, normally we just have a straight line contact. It's like this laser. It just goes in this very straight line from our radio transmitter and receiver to the one on the satellite. We talk to it. If you have more and more ionosphere, then you get refraction that bends those radio waves. And that bending of the radio waves can make us see the satellite in a different place. We have to change where our antennas point. Also, this B case is absorption. If you have enough ionization in the upper atmosphere, it absorbs radio waves. And so you get communications blackouts and disruptions, or lots of noise, reduced signal between your satellite and the Earth, and vice versa. Scintillation or scintillation is when you have blobs of ionosphere, blobs of higher and lower ionized gases, causing the transmission essentially to be twinkling. It scatters the radio waves, it causes little outages and scattered radio waves and noise all over the place. And that can be very disruptive to communications. So who cares about ionospheric effects? This shows only a few of the systems that we use today that are affected by satellite communications, by radio communications. GPS. Does everybody know how GPS works? It's built into most people's cell phones now. A lot of people have them in their cars. You can buy handheld GPS things. GPS is basically talking to satellites or listening to satellites. You have a receiver. It looks at satellites that are flying over. There are a whole bunch of GPS satellites orbiting the Earth. Your receiver looks at several satellites and does triangulation. It tells you exactly where you are within a few centimeters. If you have dual frequency GPS, you can tell even within millimeters of where you are. But imagine solar activity affecting the ionosphere, changing the ionosphere, making refraction happen, and suddenly your GPS looks up into the sky, sees a bunch of satellites, but the signal from those satellites is refracted, so that the satellite appears to be in a different place. The GPS then calculates your location to be in the wrong place. You're no longer driving on the highway. Your GPS says you're driving through a house next to that. Now that doesn't seem like a big deal for most of us in everyday life. We don't really care where we are down to a centimeter or so. But a lot of people do. Become more and more dependent on GPS to navigate things, like ships. Giant super tankers that have really deep drafts go into harbors now that have been dredged out so that they're very narrow channels. And the pilots can't always tell exactly where those channels are, and they use GPS to guide them in. If the GPS tells them they're in the wrong place, they can run aground and spill all their oil all over a harbor. That is not a good thing. Airplanes use GPS all the time. If they can't see, they use GPS in combination with other navigational aids to tell them exactly where they are. In fact, airplane pilots can throw a switch and have the airplane land itself using GPS without the pilot being able to see the runway at all. Now imagine what would happen if the GPS on the airplane thinks it's 40 meters off to one side. That airplane would land in a field or in the terminal or somewhere else. That's a big problem. Other people who use GPS are farmers, believe it or not. Now my parents and grandparents were farmers, I wasn't. But farming today is very different than it used to be. There are fewer and fewer family farms, and there are huge conglomerate corporate farms, and they have these huge fields that cover many, many, many square miles, hundreds of square miles. And they plow those fields, not by eyesight, driving their truck around to see a straight line. They use GPS to guide them. So they want to know exactly where things are, where their equipment is. People who do surveying use GPS all the time to find out exactly where property lines are. Also for a lot of geologic surveying and geologic exploration, like oil wells. They all use GPS to determine where they're drilling and where they want to drill to. And if they screw up, they can waste a lot of money drilling in the wrong place. If they know that there's an oil reserve, if they drill here and then over to the side into an oil reserve that they have the rights to, but there's a city on top of, and they miss that, they've wasted a lot of money trying to do that. So they care about GPS. The military cares about GPS. They fly airplanes all over the world. They have people in active operations in Iraq, Afghanistan, all over the world. Their ships. All of them are using GPS to tell exactly where they are and transmitting that back to headquarters. They send missiles. Cruise missiles are programmed by GPS to know where they are and where to go. And if the GPS is wrong, you can put your missile not in the Al-Qaeda nest there, but the mosque or the grade school right next door. It's not a good thing. So a lot of people care about GPS. Let's move on to other impacts. Here's a a little animation that NASA made of a coronal mass ejection. We're looking at the sun. Suddenly a flare goes off, and a coronal mass ejection comes off the sun and propagates out through the interplanetary medium, and it arrives at the Earth. The Earth has a nice, quiet magnetic field, but suddenly this big blob of plasma, charged particles and magnetic fields from the Earth disrupts the whole Earth's system, changes our magnetic fields. Particles stream down the magnetic field of the Earth and hit the Earth's atmosphere and create the aurora. Cause the auroral oval to expand, get more intense, lots and lots of activities. So let's talk a little bit about the particle and field effects from flares. First of all, when a flare goes off, you have a lot of bright light in the X-ray, UV, and such. We've talked about those effects. You can also have a burst of super energetic particles. Now, light gets to the Earth in 8.5 minutes, roughly, from the sun. These particles are so energetic and moving so fast that they take only a few minutes more up to a few hours more to get here. So these are relativistic particles. They're moving along at a good fraction of the speed of the light. And those particles, they're not CMEs. They're just things like protons and electrons that burst out of the flare. Now, not every flare has them, some do, some don't. But they can get here within minutes or hours, and they'll just basically go through everything in space. Satellites, astronauts, whatever else is up there, aliens. And we've seen satellite anomalies, we've seen failures attributed to these energetic particles. You get things like surface charging, you get computer events, single event upsets, where basically a bit flips in your computer and suddenly your computer doesn't work anymore, or it does the wrong thing. All of our satellites these days are robots in space. They have computers for brains. If you scramble the brains of a satellite, it gets confused and can't do its job very well. You also get noise in imaging system. Here's a satellite image looking back at the Earth in the ultraviolet, and one of these proton events occurs, and suddenly all you see is noise. You don't see your image anymore. And if that image is maybe a satellite that is doing weather, lose your weather information. It's a satellite that's doing military surveillance, lose all information that's going on with that. So you have to be able to protect against that. This is a headline from a few years ago, and here's another one showing the ANIK satellite, I don't know how they pronounce it, ANIK satellite. It lost control after a big energetic particle event from the sun. Essentially, they believe the satellite's brain was addled by this burst of radiation, and it could no longer do its attitude control. It spun out of control and never recovered. Other satellites, communication satellites and things, can be disrupted, and if you lose communication, that can have a big effect for a lot of people. Let's talk about CMEs now. CME, as you saw from that movie, is a big blob of plasma moving out through space. It hits the Earth's magnetic field, shakes it up, basically. So it's no longer its nice dipole type state. It rattles it up, it fills it with particles, it causes enhanced aurora, something we call geomagnetic storms. Usually these are just at the poles, but as we saw with the Carrington event, it's a really big one. Those effects can reach all the way down to low latitudes, Hawaii and the Caribbean and things like that. These geomagnetic storms can cause increased radiation at high altitudes. The aurora that we were looking at before are caused by those energetic particles following the Earth's magnetic field, going to the poles, hitting the atmosphere and exciting it. People who are concerned about that are people who fly over the pole on a regular basis, passengers and crews of polar flights. Back in the days when I was a grad student in the 80s and early 90s, we had very few polar flights. Today, there are about 9,000 polar flights a year because it saves a lot of money for the airlines to fly straight over the pole because it's shorter than flying around the Earth on the sides. If we were to fly from, say, Washington, D.C. to Beijing, China, on a regular route, the plane would have to make a stop and refuel. That costs a lot of money. Now, if they fly over the poles, they can do it in one shot. It takes about 15 hours rather than 18 or 20 hours, and they don't have to refuel. But the passengers and the crew are constantly worried about radiation. They put radiation monitors on these flights, and they redirect them if they're going through a high radiation environment. CME effects on the magnetosphere and the Earth's system also affects the ionosphere. It complicates it. It causes bubbles in the ionosphere, which cause more scintillation. It causes a lot of complicated effects at high latitudes too. And this affects GPS, as we've seen. So not just sunlight from the sun affects GPS, but the particles and fields coming from the sun affect the GPS. Now that matters to airplanes flying over the pole a lot. There's a rule that the FAA has implemented that all airplanes must be in contact with the ground at all times. And in contact with some sort of a navigation system. If that is not true, then they cannot fly the polar route. And they have to land or go around another route. That costs lots and lots of money. This increased complexity and ionization in the upper atmosphere of the poles also disrupts regular communication with radios. And this is where the rule that the airplanes have to be in constant communication with the ground comes in. If the ionosphere is enhanced at the pole and they can't no longer talk from the pole down to radio stations at lower latitudes, they have to land or change their trajectory and point some other direction. So they can't do the polar routes in high geomagnetic effect or geomagnetic storm activity levels. These geomagnetic storms also set up ground-induced currents. Now, an induced current is something that you can do with a magnet and a wire. If you wave a magnet over a wire, it will induce a current in that wire. That's how generators work. Spin a magnet in a coil of wires, and that causes a current in the wire. Well, that can happen in the Earth. The ionosphere and the magnetosphere changing rapidly are like you waving a magnet over a wire. And the ground itself, and anything attached to the ground itself, can have currents running through it. This happens all the time, but when there are big magnetic storms, you get even bigger currents induced. And people who care about that are people who have huge conductors all over the ground, such as high voltage power lines that are spread out all over the Earth, or pipelines from Alaska down to, from North Alaska down to Southern Alaska, across Canada, across the US. We have pipelines all over the place. Those are big metal conductors. If the magnetosphere and ionosphere is changing above them, you can get large currents running in those. And that can cause lots of problems. Transatlantic cables in the ocean are affected by this. Here's just a plot of some polar flights. You're looking down on the Earth, and anything that flies through this middle part of the pole is considered a polar flight. It's about 82 degrees north. And within that, they can primarily only do satellite and high-frequency radio communications. If there's a geomagnetic storm, they lose that, and they have to reroute around it. In January 2005, there was a solar event, and several flights had to be rerouted. And the impact to the airline industry was about $250,000 just for one day of rerouting these flights. Imagine if there were lots of storms. Ground-induced currents have a big effect on power grids. In 1989, that storm that I was up in Alaska watching, like, wow, biggest thing of my life, caused a lot of problems for people in Canada. Hydro-Quebec had a very large grid over eastern Canada, maritime provinces, go out because ground-induced currents in the wires were so large they burned out transformers. This is a picture of a transformer burned out by geomagnetic activity. This is a picture of a man standing next to a transformer like that. We're not talking about changing a little bitty thing. We're talking about something very large, very difficult to replace and very expensive to replace. When this transformer burned out, about 1 million Canadians lost power for a good portion of the day. Now, I haven't talked about all of these things, but you can start to imagine the level of your everyday life that's affected by space weather. Satellite communications, your pager, your cell phone. They may only talk to ground stations near you, but those ground stations talk to satellites passing around the world. So a space weather event can affect your GPS, can affect your airplane, affect you driving your car, can affect you talking on your cell phone. It can blow out transformers, you lose power for several hours. It can cause people flying in satellites or the space station or in airplanes going over the pole to have their lives disrupted at a very large expense. Yeah.
So they don't have any way of controlling this at all, do they?
We can't control the sun or how the Earth reacts to the sun. All we can do is control how we respond to it. Now, what the people who run airlines want to know what's going to happen before they launch their airplanes to fly over the pole. So they're looking for somebody to tell them a forecast of what space weather is going to be like. They want somebody like Crystal Lager from Channel 9 telling you that tomorrow we're going to have a geomagnetic storm of such and such activity. So please reroute your flights. And that's what I'm going to talk about next, actually, or right after that. Running out of time. I told you I'd run out of time. So let's muse a little bit. I've told you about just a few examples of space weather effect on our technology. Those were just normal space weather effects, things that happen on a fairly frequent basis, daily, monthly, yearly, every 10 years or so. What happens if we have a Carrington-like event? Scientists consider that to be the biggest solar event ever witnessed by humans in the technological age. And we haven't seen one that big since. It's probably at least 3, if not 10 times stronger than any other events that we've witnessed since the space age has begun. Since 1859, we've developed a lot more technology that can be disrupted. It's not just people, telegraph operators, going dee 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 dee. It's everything. It permeates our life to the very core these days. You can't turn on a light switch without actually being affected by space weather. You can't drive your car, fly in an airplane, talk on your cell phone. So what happened if a Carrington event occurred today? We call that the perfect storm. We would have widespread blackouts. There's a movie simulating that. All of our power systems are linked. We trade power back and forth between, run that again. It's not just a bunch of little companies serving an area. It's a lot of big companies all connected, trading power back and forth between grids. One grid goes down, it can pull other grids down. And we can be very vulnerable at very odd times, actually. Not the highest consumption times, but times like in the middle of the night, when it's cool, and nobody's running any electricity. That's when the companies transfer huge amounts of power between grids and move it around. And if a magnetic storm occurs then, and we blow out transformers, those transformers can bring down huge amounts of power. Now, those transformers I showed you aren't cheap to replace. They're also not a stockpile of transformers ready to go and plug in. Those transformers can take months, even years to replace. So if we burn out a bunch of them, think about the impact of that. We could lose power in areas for months, if not years, from a major event that blows out dozens of transformers. Not just one like the Hydro-Quebec case, but many. Now think about what happened in New Orleans with Katrina. They lost a lot of the infrastructure. It took a long time to recover from that. Now think if that happened on a nationwide scale, what the impact to your life would be. In addition, you'd have communications blackouts, no GPS, no cell phones, no emergency response. Emergency responders use satellite communication when infrastructure goes down to talk to each other. But if the satellite communication is also down, the emergency responders are hampered too. You have no satellite navigation, no HF radio, planes are grounded, the military's hampered. What else? You have problems on satellites themselves. You don't know where the satellites are. They can run into each other. They can re-enter early. You have communications disruptions because the satellites are having anomalies or there's noise and we can't talk to the satellites anymore. We have failures of satellites. We have maybe astronauts sitting on the International Space Station or on their way to Mars, a trip that takes a couple of years. And they can get fried, essentially. They can get the equivalent of many lifetimes worth of X-rays in a few minutes from some of these big storms. So there was a study that was chaired by the director of LASP, actually, and sponsored by the National Academy of Sciences, called the Severe Space Weather Events, Understanding the Societal and Economic Impacts. They just published that study. They did a study out of this perfect storm situation. What would happen? What would the effects be? And they estimate that the cost of such would be $1 to $2 trillion.